You know, when you picture a map, the first thing that probably pops into your head is directions, right? Getting from A to B,
Uh-huh.
navigation. But what if we thought about maps as something, well, much more powerful, like tools for uncovering hidden stories, really digging into data to find, surprising insights?
That's precisely the territory we're exploring today.
Yeah.
We're taking a deep dive into digital mapping and geographic information systems, GIS, focusing on how these technologies let us visualize information
Okay.
in ways that reveal, well, a deeper understanding.
So we're not just looking at pretty pictures of the world here. We've got this university lecture, right? 2025 data and design class 15, something like that.
That's the one. Digital mapping and GIS for visualization.
And there's some summaries too, briefing documents in English and Korean.
Got it. And our mission really is to grasp the core principles, the practical ways digital mapping and GIS help us go beyond just seeing locations
Right.
to actually getting new knowledge, those aha moments from the data. Exactly. And the source material really hammers this home, that the true power of mapping isn't just, sticking facts on a map. It's about generating insight.
Insight.
Yeah, the
Right.
briefing docs put it nicely, saying mapping is fundamentally about revealing something, pulling something out that wasn't obvious before.
Okay, revealing something. And interestingly, the lecture mentions that sometimes, well, exaggeration can even be useful to highlight
It
insights.
sounds counterintuitive, maybe,
Mm.
but yeah. Sometimes you need to make the important stuff really pop
Oh.
visually so the message is crystal clear. It's not about distorting the truth, but emphasizing a key finding.
Hmm. Can you give an example?
Well, think about a classic one. John Snow's 1854 cholera map in London.
Oh, yeah, the water pump.
Exactly.
Hmm.
By mapping where the deaths were happening, concentrated, he could visually pinpoint that contaminated water pump as the source.
Right.
It wasn't just dots on a map, it revealed the cause. That's insight. It narrowed it right down.
That's a perfect example. Solved a crisis by visualizing data.
Okay, fast forward a bit. What about Laura Kurgan's $1 million blocks project in Brooklyn?
Another powerful example. What Kurgan did was visualize the staggering cost of incarcerating people who came from very specific city blocks.
The cost of keeping them in prison, basically.
Yeah, the cost of housing inmates from those specific blocks in correctional facilities. She mapped that cost per block.
And what did that reveal?
It showed this incredible concentration of spending in just a few neighborhoods. Millions of dollars effectively being spent on incarcerating people from just one block.
Why?
It instantly makes you question resource allocation, the impact on those communities. I mean, seeing it mapped out like that so starkly.
It forces you to think differently about where the money's going and, well, the underlying issues.
Absolutely.
Okay, so to make these kinds of maps, we obviously need data. The lecture talks about different types.
It does, yeah. It touches on the basics: integer, float, continuous, discrete, ordinal, nominal data, the categories. Why does that matter for mapping?
Well, the crucial point, and the lecture highlights this, is that the same number can mean totally different things depending on the context.
Right.
Okay, take the number 2.
Right.
Right, it could be a quantity, 2 benches here,
Okay.
or it could be a rank, this is the second most crowded park,
Right.
or it could be, say, a coordinate value on a grid, a t value maybe defining a curve.
I see. So 2 isn't just 2.
Exactly. The lecture puts it, it's the same data, but it clearly has different meanings.
Mm.
And for mapping, you need to translate that raw number into something visual. Like those numbers 4, 4.5, 4, 6 don't mean much until you see them as points on a map, maybe with circles sized by the value.
Or like the binary code making a smiley face example in the lecture, turning numbers into a picture.
Precisely. Transforming numerical data into visual information. That's the key step.
Okay. And the lecture brings up another idea from someone called Minsihi
Yeah?
about visualization urging change.
Yeah, that visualization, including mapping, can be a tool to sort of nudge people towards action, to urge change.
How so?
Well, think about mapping climate change impacts, like sea level rise
Hmm.
or deforestation rates. Seeing that visually,
It makes it more real, more urgent.
exactly,
Yeah.
it can communicate the scale and severity in a way that tables of numbers might not.
Yeah.
It reinforces that mapping is about recording, yes, but also communicating effectively.
Makes perfect sense. A good map tells the story. Okay, let's get into the nuts and bolts. The GIS data structures. What's foundational?
Well, GeoJSON is mentioned as really important. You should think of it like a a digital standard for holding geographic info.
Okay.
It's based on JSON, which uses key value pairs, kind of like Python dictionaries, if you know those, simple text format.
So it's structured data for location.
Exactly. The lecture says it was basically created like, this is how they created GeoJSON to handle geographical information in this way. It's designed for the job.
And there was an example.
Yeah, they showed parsing GeoJSON data for earthquake locations worldwide, visualizing them on a 3D globe. They could even make, like, spikes stick out based on the earthquake's magnitude.
Oh, cool. So you can see the intensity visually.
Right. That structure makes it easy for computers to analyze spatial stuff, find patterns you might miss otherwise.
Okay, GeoJSON. What else? Vector data comes up a lot.
Ah, yes, vector data. Fundamentally, it boils down to three things: points, lines, and polygons.
Points, lines, polygons.
Yeah. A point is just a single spot, maybe a bike parking location, like the Boston example they showed from a CSV file.
Okay.
A line is, well, a line like roads or rivers. They used OpenStreetMap data for roads, as an example.
Makes sense.
And a polygon is an area building footprints, land use zones, that kind of thing. Again, they showed examples from OpenStreetMap.
So those three are the building blocks.
Pretty much. The lecture really stresses this.
Meaning you can basically cover GIS with just these three. Understand points, lines, polygons, and as they put it, your GIS is excellent powerful.
So simple shapes, but you combine them to model the world digitally.
That's the idea, and the relationships between them hold the stories. What about other types? Raster data, shapefiles.
Right. Raster data is mentioned briefly. That's pixel-based, like satellite images or elevation models, which might have come up before when discussing image processing.
Okay, grids of values.
Exactly. And shapefiles, .shap files, they're another really common format from Esri. Often comes as a bundle of files, not just one.
Right, I've seen those.
The lecture showed visualizing a forest polygon shapefile and actually suggested converting shapefiles to GeoJSON sometimes, just because GeoJSON can be easier to work with in, say, web development.
Good tip. And OpenStreetMap, OSM.
Yeah, definitely important. It's huge.
Yeah.
A collaborative open source map of the world. People contribute data constantly.
So you can just pull data from it.
Yep. The lecture demonstrated importing maps straight from OSM showed roads and buildings for the presenter's university campus. Very useful source.
And digital elevation models, DEMS.
We touched on that with raster, but yeah, specifically for showing terrain, the shape of the land,
Yeah.
hills, valleys, crucial for landscape stuff.
Okay, so we have all this data points, lines, polygons, rasters in different formats like GeoJSON or shapefiles. What can we actually do with it in a GIS?
Ah, right. Geoprocessing operations. Think of these like modification tools in CAD software, but for maps.
Like editing the geographic data itself?
Exactly. The lecture covers some key ones. There's union, which combines overlapping areas into one.
Okay.
Then merge and dissolve. They both combine features, but they're slightly different. The lecture explains. Merge adds the entire areas, while dissolve ties together the areas within based on the same properties.
So merge just lumps everything together.
Pretty much. While dissolve is smarter, it combines adjacent polygons if they have the same attribute, like maybe merging several forest patches into one big forest area if they're all classified the same way.
Got it. Dissolving based on properties. What else?
Intersect finds where features overlap. So if you have a layer of flood zones and a layer of residential areas, intersect shows you which houses are in the flood zone. Clipping is like using a cookie cutter. You define an area and cut out just that part of your data.
Okay.
And buffer, this one's really common. You create a zone around a point, line, or polygon, like draw a 500-meter circle around a school or a 10-meter zone along a river.
What's that used for?
All sorts of things. The lecture mentions selecting areas near points or lines. It also has real-world uses in navigation, like figuring out if your GPS position is actually on the road network by buffering the road line.
Ah, clever.
Yeah, and there was a neat demo in the lecture drawing rectangles on a map and instantly seeing calculations like how many commercial or residential buildings were inside the box or excluding certain zones.
Wow, real-time spatial analysis, like for planning or funding allocation.
Exactly. Super practical application of these operations.
Now, you mentioned GIS data can get huge, especially for big areas. How do we handle all that detail?
Right, that's where map generalization comes in.
Yeah.
It's basically simplifying the map representation without losing the key information. Especially important when you zoom out.
You don't need every tiny wiggle in a coastline when you're looking at the whole country.
Precisely. So there are algorithms like Douglas Pucker or Vis Valium Wyatt. The lecturer mentions these that reduce the number of vertices, the points defining lines and polygons, makes the data lighter, faster to draw.
So it smooths things out intelligently?
Yeah, based on preserving the overall shape. The presenter mentioned using them in their smart drawing app to optimize data.
Okay. Any other techniques?
Clustering is another one. If you have loads of points really close together, like maybe restaurants in a downtown area, when you zoom out, you might represent them as a single cluster symbol instead of a messy blob of dots.
Kind of like Gestalt principles we discussed before, grouping things visually.
Yeah, there's a connection there, the lecture notes. In the case of GIS, the data can become extremely large. There are ways like this generalization to handle it.
Makes sense. You need ways to manage the complexity. Okay, another big challenge. Projection. Putting the round Earth on a flat map.
Always tricky. Yeah, the lecture explains that any flat map of the Earth has to distort something shape, area, distance, or direction. You can't preserve everything perfectly.
So different maps distort different things.
Exactly. Different map projections prioritize different properties. The famous Mercator projection, the one Google Maps uses, for example.
Right.
It preserves angles locally, which is great for navigation, but it massively distorts areas, especially near the poles. Greenland looks enormous.
Yeah, I've seen that.
So as the lecture puts it, regarding mapping, with each projection, did we prioritize angles or did we prioritize area? We had to sacrifice one. It's a trade-off based on what the map is for.
A fundamental choice map makers face. Okay, so what tools do people actually use? Software, libraries?
There's a whole ecosystem. For web stuff, you've got big platforms like ArcGIS Online, Mapbox, also powerful libraries like deck.gl, the lecture mentioned. Tesla uses that.
For visualizing their data, presumably.
Yeah. Then for desktop software, there's the industry standard ArcGIS Desktop, but also a fantastic free and open source option, QGIS. Really powerful.
QGIS. Okay. Good to know there's a free option.
Definitely. And for 3D visualization, 3JS is mentioned as a versatile library. Plus, more basic 2D canvas libraries for simpler web maps.
And the lecture showed dynamic maps.
Yeah, zooming in and out, and the features roads, buildings redraw themselves appropriately for that zoom level, showing more detail as you zoom in, simplifying as you zoom out. That's generalization in action.
Very cool.
And crucially, the lecture points to a GitHub repository with code examples. Working with CSV, GeoJSON, OpenStreetMap data really encourages people to get their hands dirty.
That's great. Practical resources are key. Now, beyond just static maps, what about making them more alive, interactivity and animation?
Absolutely. That adds another layer of engagement and understanding. Interactivity lets users, click on things, query the data, filter what's shown.
Like clicking an icon on the map and getting info.
Exactly. Linking the visuals to the underlying data dynamically. And animation. Well, that can show change over time, like urban growth or traffic flow. Or it can tell a story by guiding the viewer through different map views.
How is animation done?
The lecture mentions keyframe animation as a basic technique to find the map state at frame 1, frame 10, frame 20, and the computer figures out the steps in between.
Smooth transitions.
Right. There was an example mentioned of a company project animating map data frame by frame to show movement. And another interesting one, a web page where scrolling changed the background map and elements, telling a story about a place as you scroll down.
Oh, that sounds like a really neat way to integrate maps into storytelling.
Yeah, very engaging.
Okay, so for listeners who are now intrigued and want to dive in, what are the practical next steps recommended in the lecture?
Number one is definitely check out that GitHub repository. Play with the code examples reading CSV, GeoJSON, OSM data. That hands-on part is vital.
Get comfortable with the data formats.
Exactly. Then try using QGIS since it's free. Or if you're using Grasshopper like in the lectures demos, try the components shown for reading those earthquake files. The OSM city data, Seoul, Boston, the forest shapefile.
So practice parsing and visualizing different data.
Yes. Understanding how to get data in from different sources is fundamental. And the lecture emphasizes, especially if you're interested in urban data, these skills are really valuable.
And it connects back to earlier concepts, too.
Right. It reminds us about things like the lie factor, data ink ratio, avoiding chart junk, maintaining graphical integrity. Those principles of good visualization still absolutely apply to maps.
Okay, so let's wrap this up. What's the big takeaway from this deep dive on digital mapping and GIS for visualization?
I think the main message is that these tools, digital mapping and GIS, they go way beyond just showing you where things are. They're powerful analytical tools for extracting real insights from spatial data.
Finding the hidden stories.
Exactly, and then communicating those insights effectively, visually.
And it requires understanding the data, the techniques like projection and generalization, and applying those principles of good visual communication we've talked about.
Couldn't have said it better myself. It's a mix of technical skill and critical thinking about the data and how you represent it.
So for you listening, maybe the next step, besides checking out the resources, is to think about a map you use often.
Yeah, consider what data might be behind it, what stories are hiding in there. How could visualizing it differently maybe reveal something new? Or even inspire some kind of action or change? What questions could a different view help you answer?